My name is Joao Magueijo. I'm a cosmologist. My job, my obsession, is to work out why everything works the way it does. For the past 20 years, I've been trying to make sense of the universe. In the process, I've been called an anarchist, a heretic, a radical, even a moron. Welcome to this crazy world. Hey, I know what happened at the beginning of time. I've spent most of my adult life trying to unlock the secrets of the universe, attempting to uncover the forces controlling billions of galaxies. This investigation of time and space is called cosmology. Cosmology is physics on a mind-bogglingly large scale, the scale of the entire universe. As such, it has to answer some radical questions. Why are we here? Where are we going? Where did all this come from? To these questions, modern cosmology replies with two words: Big Bang. The Big Bang theory is the cornerstone of cosmology, a landmark attempt to explain how the cosmos came into being. Yet, there are still mysteries at the very heart of it that send shockwaves through the scientific world. In its simplest form, the Big Bang model suggests that the universe came into being in an unimaginably hot and dense state, and has been expanding and cooling ever since. The Big Bang theory not only explains how the universe began, but why it behaves the way it does right now, minute by minute, second by second. We cannot produce little Big Bangs in the laboratory, and we were not there to see it happen. However, cosmologists are confident that it did take place because faint echoes from these initial moments still linger on in the current universe. To understand how these echoes were produced, we have to rewind time 13 billion years, to the beginning of everything. Back beyond the formation of the Earth, 4.5 billion years ago. Beyond the 10 billion year lifespan of a third-generation star like our Sun. Back to the 0 hour, when time and space began. Now the search can begin for the origins of those Big Bang echoes. It all started 10 to the minus 43 seconds after the Big Bang. That's a decimal point, 42 zeros, and a 1. A period of time so minute, we don't have the technology to measure it. At this time, the temperature was 10 to the 32 Kelvin. That's zillions of times hotter than the heat given off by a supernova. When a dying star goes supernova, it can radiate as much energy in a few weeks as our Sun would emit in 10 billion years. But that is only a tiny fraction of the temperature of the early universe. At such incredibly high temperatures, matter is really dense, is very concentrated, so that there's no way light can get away from its influence. It's imprisoned inside matter. The energetic photons of light are trapped amongst the densely packed particles of matter, with no means of escape. Everywhere the photons turn, matter blocks their path. The young universe is completely opaque. No light can escape from it. It's just like what happens, say, inside the Sun. The Sun is a huge sphere made almost entirely of the gases hydrogen and helium, more than 1 million kilometers in diameter. But even though it consists of gas and little else, the Sun's interior is opaque. You can't see through the Sun because the temperature inside is so high and matter so concentrated that light is trapped inside it. What you really see is the surface around it where the temperature drops sufficiently that light suddenly is free and can travel towards us. Exactly the same processes were at work in the early universe. For 375,000 years, light was trapped inside matter. But as the universe aged, as it became cooler, eventually the temperature dropped below 3000 Kelvin, when the density of matter is no longer sufficiently high to trap the light. At last, the light could escape the matter. And then, suddenly, there was this big burst, this tremendous burst of free light. The first free light in the universe. In fact, so intense was this burst that this light should still be around, carrying with it information. Secrets from the very earliest stages of the universe. But if this primordial light is still around, why can't we see it? All we see is darkness, dotted by stars. Even if we get a telescope, all we see is more darkness, dotted by more stars, and things like galaxies, clusters of galaxies. So much for the Big Bang. Well, not quite. The key for finding something is knowing how to look for it. At this point, it might be useful to think of light as shrimps. Why not? Shrimps are just as much part of the universe as stars or galaxies, subject to the same basic physical forces and laws. As far as I'm concerned, there's no aspect of cosmology that can't be explained by everyday things around us. Shrimps, like this one, come from a large family of crustaceans. At one end of the scale, you get half-meter-long lobsters. At the other, you get tiny krill. All built on the same model, all with similar behavior and taste. Likewise, light comes from a family of rays called the electromagnetic spectrum. You get kilometer-long radio waves at one end of the scale and tiny gamma rays at the other. All built on the same model, with similar behavior, traveling at the same speed. A lobster is basically a stretched-out shrimp. A radio wave is basically stretched-out light. As the universe expanded, that primordial light from the Big Bang was stretched out into radio waves. So if you're looking for those primordial echoes from the Big Bang, you should not be looking for visible light at all. You should be looking for radio waves. Of course, we can't see radio waves. Our eyes can only sense a tiny portion of the electromagnetic spectrum, visible light. But there is a machine that allows us to see these signals from the Big Bang. This machine is not a high-powered supercomputer or an enormous telescope on a remote mountaintop. It's something much more straightforward. Television. Television allows us to hear and see this stretched out light, the cosmic microwave background. I know it sounds crazy, but the Big Bang is on another channel right now. Switch your TV set over to an untuned channel. Not right now, you're listening to me. But when you do, you will see a lot of static. About 1% of this static is the cosmic microwave background, or CMB as we call it. This is stretched out light directly from the beginning of the universe. You are now seeing echoes from the Big Bang, the most important event that ever happened. Not in a government lab or a particle accelerator, but in the comfort of your own home. The Big Bang and its echoes are part of everyday life. Of course, static has been around since TV was invented. We just did not understand what we were seeing. Now we see it for what it really is. Signals whizzing around from the beginning of the universe, proving that the Big Bang did take place. The discovery of the cosmic microwave background was central to the Big Bang theory's acceptance as the best model for the origin and evolution of the universe. But these radio waves, the CMB, turned out to have even more significant implications. If we examine the CMB closely, we find that it has minute variations in its temperature. And if we make a map with these variations, we get this. It's a snapshot of the baby universe shortly after it left maternity, the Big Bang. But for cosmologists, this abstract painting is the most significant discovery of all times. It's called the W-map picture, after the Wilkinson microwave anisotropy probe, and it got us very, very excited. If these pictures had turned out to be just one color, then we would not be here. The universe would be a mush, a completely uniform soup without any variations. On the contrary, we find these tiny fluctuations, these tiny lumps. They really are the blueprints for the structures that emerge later in the universe: galaxies, stars, and us. Like every other cosmologist, I've spent hours and hours scrutinizing this blueprint for the universe. According to the Big Bang theory, there should be no pattern to the distribution of different temperatures across the sky. But I found that there did seem to be some order to the arrangement of these fluctuations. The pattern is so subtle, it only emerges when the complicated W-map picture is broken down into a series of more simple temperature maps. The Big Bang theory predicts that the universe is the same everywhere, and the arrangement of the different components should be completely random. But it isn't. Some of the temperature maps turn out to have features in common. They align along one special direction, which I dubbed the axis of evil. I called it the axis of evil because it implies there is a flaw in the Big Bang theory. Some people thought I was seeing things that weren't there. But complex statistical analysis proves that these alignments aren't just due to chance. The axis of evil really is present in the data.
No one really knows what this means.
The significance of the axis of evil is still a mystery.
Perhaps it's merely a mistake in our instruments, or it could be a real feature which the Big Bang Theory cannot account for.
As demonstrated by the Hubble shrimp, the CMB started life as the first light in the universe and was gradually stretched out into radio waves as the universe grew older. The process behind this stretching provides further support for the Big Bang Theory.
The stretching of the primordial light into radio waves occurs because the universe is expanding.
This expansion is a phenomenon that seems to be taken for granted, and that's just not good enough.
How do we actually know that the universe is expanding?
The first blinding burst of light produced by the Big Bang still echoes through the cosmos, 13.5 billion years later. Not as light rays, but as radio waves known as the CMB. The only explanation for the stretching of this light into radio waves is that space is expanding. How do we know this is going on? The answer comes from our recent observations of galaxies.
Every direction in the sky is full of galaxies, and every single galaxy is moving away from us. Is then the whole universe trying to avoid us? Are we the center of this big cosmic explosion? Mankind has always had the hope that everything revolves around us. But it only takes my grandmother's cosmic knitting to disprove this fact. Every year, my grandmother knits me a jumper for Christmas. She does it for all of her grandchildren, all 25 of us. Each jumper has a pattern to suit the wearer.
My sister is a farmer, so she gets a horse. My cousin George used to collect golf balls. Christina has a pollen allergy. Renata once dated a clown. Carla loves military hardware. This is Sergio. He once broke his ankle skiing. And my cousin Lucia keeps chickens. Each year brings another astonishing collection.
Because I'm a cosmologist, I always get jumpers with complicated patterns representing what she thinks is the universe.
Here's the latest offering.
Apparently, each of these buttons represents a galaxy, and the knitting in between them represents the fabric of space. If I stretch out the jumper by putting it on, space expands.
Carrying the galaxies with it, they all end up much further apart than they were to start with. The distances between the button galaxies have increased dramatically. From a universal perspective, it's very clear that not one of them has stayed motionless at the center of the expansion. But from the point of view of a single button, like this red one, it looks as if every other galaxy has moved away from it, leaving it at the center of an ever-increasing void.
The point is that the universe is getting bigger. The distance between galaxies is increasing. The space in between them is expanding.
Our galaxy is not the center of this expansion, just a part of it.
And this expansion is yet another lingering proof that the Big Bang did take place.
And that's important for what comes next.
If the galaxies are all flying apart, it follows that at some time in the past, they all jumped together. It's like dropping a jar full of marbles.
In an instant, Everything goes from being tightly packed together to flying apart at incredible speeds. The direction and speed of the marbles carry valuable information about the moment of impact. Similar information can be gleaned from the speed and motion of the galaxies in our universe.
If we extrapolate backwards, we find that this moment in which everything was together happened 13 billion years ago, the time of the Big Bang.
It seems that the more we look at the universe, the more evidence we find to support the Big Bang theory.
By recognizing the CMB for what it is,
Stretched out light from the earliest stages of the universe,
and by discovering that space is expanding, cosmologists were able to prove that the Big Bang is indeed a convincing explanation for why everything looks and behaves the way it does. But nothing is perfect. And like every good cosmological theory, the Big Bang is not flawless.
its flaws provoke some of cosmology's fiercest debates.
To understand where these flaws come from, we have to go back to the beginning. Not the universe's beginning, but mine. I was born in Évora, Portugal in 1967.
I like chocolate, playing soccer, and teasing my sister.
I didn't like school or spinach. Two streets away lived another boy of my age named Felix. Felix went to a different school, played with different kids, supported a different soccer team. Although we started life in the same town at around the same time, we never met. Just before my 5th birthday, my family moved away from Évora. For the past 40 years, Felix and I have led entirely separate existences. So if you had to guess what Felix looks like now, what would you say? You'd be crazy to think that Felix is also 1 meter 80, weighs 85 kilos, and is a physics professor with subversive ideas about the speed of light.
And of course, he isn't.
Felix is fat, bald, and is a butcher.
Today, he and I have virtually nothing in common, apart from the fact that we were born around the same time in the same region. It's exactly the outcome you'd predict.
But that kind of logic doesn't seem to apply in space.
If the basic Big Bang model is correct,
Opposite corners of the universe are so far apart that light, and nothing can travel faster than light, hasn't ever had the time to travel in between them in the 13.7 billion years since the Big Bang. They've been completely out of touch and should be utterly different, just like Felix and me. Observations, however, show them to be identical, a feature which the Big Bang theory simply cannot account for.
it's as if Felix grew up to be like me in every single way.
This unexpected Felix outcome is more properly known as the horizon problem.
And it's a major problem. According to the standard Big Bang theory, there is absolutely no way these distant parts of space could ever have exchanged information of any kind. They are, always have, and always will be outside each other's horizon. Yet, the temperatures and other physical properties are too similar for them not to have been in contact at some stage. It's understating the issue to call this significant flaw the horizon problem. From the Big Bang theory's point of view, it's a catastrophe.
Whatever you call it, it's one of the greatest mysteries of our universe. The job of cosmologists like me is to find solutions to this problem while at the same time trying to preserve as much as possible the good bits of the Big Bang theory.
Namely, that space and time, the universe, began in an unimaginably hot and dense state 13.5 billion years ago and has been cooling and expanding ever since. There have been many attempts to solve the horizon problem, some more convincing than others.
One of the most popular fixes of the Big Bang theory is called cosmic inflation. And it works like this. Three weird-looking people are caught on security cameras in 3 different locations of the same city. These guys are kilometers apart, yet they are covered in the same distinctive bright orange paint. It turns out that 10 minutes ago, a paint balloon fell from the sky into the city center. It plastered everyone within a meter of its impact point in this particular bright orange. So it follows that these 3 people must have been close together near the point where the balloon dropped. But there's only one problem with this idea. At a normal pace, a person can walk about 1 kilometer in 10 minutes. Yet, these individuals are kilometers apart.
Too far apart to have been together at the impact point 10 minutes ago.
But they are covered in exactly the same color paint.
So they must have been there.
This tension, this paradox, is called the horizon problem.
And it's only by finding a solution to the horizon problem that we can properly understand why the universe looks and behaves the way it does. So what aspect of the universe can be tweaked to sort this out? To rescue the Big Bang theory, cosmologists must work out why regions of the universe, too far apart to have ever been in contact, have so many similarities. Think about it this way. How can we explain three people covered in orange paint who are too far apart to have been at the site of a paint bomb 10 minutes ago?
We can't change present reality. Three individuals kilometers apart, covered in exactly the same color paint. And we can't change the time at which the paint balloon fell 10 minutes ago. But we can change the rate at which they diverged away from the impact point. A short-lived but incredible burst of speed away from the impact point just after the balloon fell does the trick.
By running from the impact point, the three victims move a huge distance from the scene in a very short time. When their pace slows to a walk, their final position and speed give no hint that they were ever at the impact point. Only the paint gives the game away.
And likewise, some cosmologists believe the early universe went through a similar burst of speed just after the Big Bang. This modification to the Big Bang theory is called cosmic inflation. It solves the horizon problem without messing up with the good bits of the Big Bang.
Inflationists believe that this sudden, massive expansion of the young universe didn't last very long. A tiny, immeasurable fraction of a second. But in that time, the universe expanded in size by a factor of at least 10 to the 26.
A surge of growth just after the Big Bang would mean that distant corners of the universe were once together, explaining their uncanny similarity.
It seems the horizon problem is neatly solved.
Break out the champagne, cosmic inflation has saved the Big Bang from embarrassment. The only problem is, there is absolutely no observational evidence for cosmic inflation.
None at all.
And believe me, people have been looking for it. Evidence, proof by observation, is really what science is all about. Without it, it's all just theories, waffle.
You might think that without observational evidence, cosmologists would find it hard to accept inflation theory as the solution to the horizon problem. But within cosmology, there has been widespread acceptance of this useful but unprovable theory.
In fact, if you read the small print, quite a lot of cosmology is just theories. Theoretical physicists, like myself, are doing nothing but playing an elaborate guessing game. It works like this. I see a cat going inside one end of a drain pipe. Then I see an unsuspecting mouse going into the other end. I hear a squeak, a meow, and a crunch. As a person with a good grasp of the behavior of cats and mice, I can come up with a theory for what happened inside that drain pipe, even though I didn't actually see it. My theory is that the cat caught the mouse, ate it, and found it very tasty. Of course, because I didn't actually see what happened inside the drain pipe, this is only a theory. Anyone else is perfectly entitled to propose a competing theory based on the same evidence. They may decide that the mouse is a fighter. They may notice that the cat came out with a limp and argue that the mouse fought off the cat and is alive and well. The game is on. It's up to anyone interested to provide the evidence in support of their theories. The debate can rage for years, with new evidence pushing theories one way or the other. The beginning of the universe is like the cat inside the drain pipe. Because it took place billions of years ago, we can't exactly see what happened. But we can use the clues, the CMB and the expansion of the universe, to produce theories. Cosmic inflation is just one theory for what happened inside that drain pipe. Other theories have been proposed, only to disappear into obscurity. So I'm entirely entitled to come up with my own solution to the horizon problem. Which is exactly what I did. I came up with this solution after one of the best parties I've ever been to. The next morning, I was walking in the rain, feeling awful. Terrible headache, a dreadful taste in my mouth. But there were fireworks in my brain. You never have your best ideas in your office. Don't believe what they tell you in school.
The theory I came up with on that cold, wet day shook the world of mainstream science. I don't think you have to be stuck behind a desk in an office or lab to have good ideas. I came up with a new solution to the horizon problem walking across a muddy field in the pouring rain.
If you need further proof, I developed some aspects of this theory
On vacation in Goa.
I call it VSL, for varying speed of light. Although some of my colleagues claim that it stood for very silly. One of the central tenets of modern physics is that light traveling in a vacuum is the fastest thing there has ever been and will ever be. Nothing can travel faster, no matter how hard we try. We can slow down a light ray by making it go through a medium, such as water or glass. But in a vacuum, light always travels at the same speed, 300,000 kilometers per second.
Or 186,000 miles per second. Fast enough to circle the Earth 7.5 times in a single second.
We keep on getting this figure no matter when, where, or how we measure it. In fact, so confident are we that this speed is a constant that we use it to define the meter.
Since 1983, 1 meter has been defined as the distance traveled by light in a vacuum during 1/300 millionth of a second. This definition works perfectly well if the speed of light truly is constant. But I'm not so sure it has always been this way. And it was this doubt that led me away from the mainstream of science. To understand VSL, you have to be prepared to see light in a new way.
Imagine light as a greyhound, racing around the track in a hot pursuit of that elusive bunny. Its owner will tell you there is a maximum speed of dogs. They cannot go any faster. Their paws would snap, they'd overbalance, they'd crash with their faces on the track. As the greyhound races around the track, it's surrounded by other dogs, all subject to the same maximum speed of dogs. But then one day, something surprising happens.
Blink and you'll miss it.
Is it a bird? Is it a plane?
No, it's Superdog.
Jet-propelled, it travels at speeds other dogs can only dream of. Just because there is one maximum speed of dogs, it doesn't mean it has always been and will always be the same.
And I believe the speed of light is similarly variable.
I think in the early universe, the speed limit, the speed of light, was much, much higher, allowing information to whiz around the universe, putting all the universe into contact.
This would mean that those incredibly remote, yet strangely similar corners of the universe at the heart of the horizon problem had once been in contact thanks to this ultra-fast light. Their similarities are now explained.
The horizon problem, then, rather than being a paradox, becomes a natural outcome.
Of course, if light is traveling ultra-fast, putting everything in contact, there is no need for the universe to undergo a sudden spurt of growth to solve the horizon problem. Cosmic inflation is simply not necessary in a VSL universe.
VSL renders cosmic inflation redundant, while at the same time keeping the good bits of the Big Bang. But this theory really annoyed a large number of people. Firstly, the proponents of cosmic inflation would spend all their lives trying to get their little fix for the Big Bang theory accepted. And secondly, all those physicists who like their constants to be constant and who couldn't quite come to grips with the fact that perhaps these constants were a bit more flexible, more accommodating. You can't really blame them for that. For decades, they've been using the constancy of the speed of light in hundreds of equations used to describe fundamental aspects of our universe. They called it C, and they used it to calculate everything. Lorentz transformations,
Electric fields, tidal stresses around black holes, black body radiation, Hawking radiation, black hole entropy,
the works. So it's not surprising that they were annoyed with my suggestion that the speed of light perhaps was not a constant. Particularly since if VSL is correct, even the daddy of all the equations, E equals mc squared, may have to be rethought. And that, as we know, means revising the whole of Einstein's theory of relativity.
and that's why they called me a heretic.
But there is nothing wrong with having a new theory. As the cat in the drainpipe shows, that is what cosmology is all about.
After all, there was a time when the existence of primordial light from the Big Bang was just a theory, until cosmologists worked out what to look for. The cosmic microwave background had been there all along, right under our noses, and it turned out to contain vital clues about the earliest stages of the universe. The discovery that every detectable galaxy was receding from Earth proved that space was expanding. Combined with a wealth of information from the CMB, this is proof enough to make the Big Bang Theory the best and most widely accepted explanation for why our universe looks and behaves the way it does. The biggest fly in the ointment is the horizon problem. the fatal flaw in the story of the universe, and the stimulus for radical new ideas such as cosmic inflation and VSL. Now it's time for my theory of the varying speed of light to prove itself against all other theories devised to solve the horizon problem.
So all I have to do now is find the evidence, the observations, that will prove or disprove this theory.
The clues I need are out there somewhere in the cosmos. They may be closer than I could ever imagine. I just have to know how to look.
And if it doesn't work out, who cares? I've got a million other ideas.